Hey there, welcome to part 3 of my video series on applications of differential equations. So part 2, if you haven't seen it, you need to see it before you try to work out what we're doing here, because a lot of the information that you were given kind of set up the problem in the second video. But presuming that you've seen all of that, we're going to go ahead and move on. Now, at any point when you're watching these videos, I strongly encourage you to pause the video and try to work the problem out in advance and see if you're able to get the same answers that I am. So moving on to the remainder of the notes, as Dan hit the ground, he rebounded straight back up into the air with a velocity of 80 feet per second. So I'm assuming that it's going to look something kind of cartoonish, where Dan fell down, hit the ground, and then bounced and bounced and bounced until he kind of, stopped hitting the ground. And they're telling us that after he hit the ground, he bounced upwards with this 80 feet per second. So that's going to give me some critical information that I need. In this case, the initial velocity, V naught, for this is going to be 80 feet per second. And that's really important information, because we established in the second video that we had to create the velocity and acceleration, or velocity and position functions, in order to be able to answer the question. Well, now that that has stopped, he hit the ground, and now he is moving again in a different capacity, we're going to have to create new equations based off of the new information. So how high did Daniel fly into the air on his rebound? So because it's asking how high did he go, that is going to be referring to a position function, s of t. So I'm going to have to use the velocity function to create an acceleration, or to create a position function, so I know how high he was at a particular point in time. So this implies that we are going to have to know some value of time, and we have to have a velocity function to create the position function, so that way we can actually answer the question and find his position of how high he was at a particular point in time. So what do we know? How can we create a velocity function with this information? Well, we know we're dealing with feet per second. So because we're talking about feet, I know that gravity in this case is going to be negative 32 feet per second squared. So that's, negative 32 is my gravitational constant. Well, if I'm looking at just a velocity function, v of t would be negative 32t plus whatever the initial velocity is, v naught. And in this case, we know that. So I have a velocity function, in this case, v of t, to be equal to negative 32t plus the 80 feet per second that he bounces back up into the air with. So we will have a velocity function now, and if I set that equal to 0, I can find out what is the time associated with this particular function. So I set the velocity equal to 0 and solve. So negative 32t plus 80 is equal to 0. Move the 32 to the left side, so it becomes positive. Divide, and 80 divided by 32 will be 2.5 seconds. So now we know what the time that we need for our position function is going to be. Now we just have to figure out what is the position function, which isn't going to be terribly difficult to do with our antiderivative process for integrals. We know that the the position is going to be the integration of the velocity function. And so that's exactly what we're going to do. I'm going to take the integral of the velocity function, negative 32t plus 80, all of it multiplied by dt. And when I do that using the antiderivative process, the reverse power rule, we're going to get negative 16 t squared plus 80t, and we have a constant because we're doing an indefinite interval. Now in this case, what is that constant going to be? So here, because thinking about the problem, he fell down and he hit the ground and he bounced back up 80 feet or at a velocity of 80 feet per second. So because he hit the ground at this point here, the initial height is going to be 0. So in this case, C would be the initial position, which in this case is going to be 0 feet because he's starting from when he hit the ground. So that will give us our position function to just be s of t is equal to negative 16 t squared plus 80t. We don't need to put the plus 0 unless you really want to. So we have the time that we figured out by solving the velocity function, and we did the antiderivative of the velocity function to create the position function. Now we can just take that information and plug it into or take the time that we got from velocity and substitute it into the position function. So I'm going to get s of 2.5 is equal to negative 16 times 2.5 squared plus 80 times 2.5, and typing that into our calculator, uh, his position at 2.5 seconds would be equal to 100 feet. So that's how high he bounced uh, after hitting the ground and rebounding with a velocity of 80 feet per second. So moving on to the next problem in our notes. So he bounced up and down for a little bit, and he finally slowed down enough to make a getaway. Secret Service is closing in, and he knows he doesn't want to get arrested because he was being silly. But anyway, Daniel knew that he could outrace them if he could get to his friend's car. So he's just really showing good judgment here. But the friend's car is a nice, fast car, and it tells us they accelerated from 0 to 4 or 0 to 60 miles per hour in 4 seconds, assuming constant acceleration. So how much ground did they cover in those 4 seconds? Now, all of our functions that we've been working with so far for position, velocity, acceleration, they've been in terms of feet per second. And now we have a unit in terms of miles per hour. Now, previously, the last question at the end of video 2, we had to convert something from feet per second into miles per hour. So in this example, we're going to take the acceleration function and kind of do it backwards, and we're going to change it from miles per hour into feet per second. So that's one thing that we need to make sure that we look at. And then it says, how much ground did he cover in those 4 seconds? So this bit here, how much ground, we're talking about a position, so we have to identify what the position function is going to be in order to show how much ground he actually covered. So let's start off by looking at what we know for acceleration. I know that for my acceleration function, we are going 60 miles per hour in 4 seconds. And we need to be able to convert that into feet per second. So taking the 60 miles per hour over over 4 seconds, we can convert that into 15 miles for every 1 second. And I'm going to multiply that by, let's go ahead and look at the time. We have 1 hour for 3,600, 3,600. Okay, let's just make this whole thing again. 1 hour has 3,600 seconds in it. And now let's look at the time. I'm sorry, not the time, but the distance. In 1 mile, there is 5,000 280 feet for 1 mile. And now let's see what units do. So here, miles and miles simplifies in the problem, and uh, the hours, where did I have hours? Hours are going to go away somewhere. I don't remember where I needed to have hours, but let's see. Somewhere I have hours that are going to cancel out. I'm just not seeing where it is right now. I apologize. But anyway, we're going to take the 15, multiply it by 5,280, and then divide that by 3,600, and that will give us a acceleration function in feet per second of, and we see here seconds and seconds in the denominator are going to give us 22 feet per second squared. So that is going to be our acceleration function. Now that's not in terms of time, that's just 22. It's just a number 22, but the you know context is going to be feet per second squared. We don't have any variables here. So we need to be able to get the position function, because we're talking about how much ground did they cover. So we have to go through the process of we can't go directly from the acceleration function to the position function. We have to get the acceleration function or the velocity function in the meantime in order to get to the position. So I'm going to say v of t is going to be equal to the antiderivative of the acceleration function. So that will give us the integration of 22 dt. So the velocity function will be 22t plus a constant. And because we're not actually doing anything with the velocity function, we really don't need the constant. We're going to kind of just continue doing anti-derivatives here. So let's do purple here, I guess. Now we can say the velocity function, now we can say will be used to get the position function. So I will say the integration of the velocity function like so. So we have the integration of 22t times dt. So my position function, when I do the antiderivative process here, will give me 11t squared plus a constant. Now in this case, the constant, the initial position, we can say the initial position is just wherever he is. That's just at 0, because if you look at it in terms of a kind of a graph, wherever you start at 0 in terms of time, and here we have distance, because wherever we start for this function, we're starting at time 0, so my value for c in this case is just going to be 0. So we have a position function of 11t squared, so I have s of t to be 11t squared, and now we want to be able to know how far did he go in those 10 seconds. So here I'm going to say s of 4, and we'll say 11 times 4 squared, so 11 times 16 gives us 176 feet in the 4 seconds. And the last problem that we're going to be taking a look at in terms of how we apply differential equations, which again, in a lot of ways, we're just, we're not really doing so much with differential equations as opposed to, maybe just doing an integral or a derivative of something to find a position or a velocity function. So the last question here says, video evidence shows Dan drove in a perfectly straight line which is amazing, from the Washington Monument across Constitution Avenue, and he crashed into the Smithsonian. which if you've never been there, I highly encourage that everybody try to go visit that at one point in their lives. He remained unscathed because a fluffy, woolly mammoth got the brunt of the impact. Uh, from the video, it could be seen that Daniel covered a total distance of 5,000 feet, so that's important information. We want to identify it, in a span of 30 seconds. So before the crash, so 5,000 feet in 30 seconds. Now we have a police officer there, which also is a former calculus student, and wants to add a charge of speeding in excess of 100 miles per hour because, you know, why not? Let's just throw the book at poor Dan here. He's made a series of bad choices. He should be punished for them, right? Explain how we can be sure that the instantaneous velocity warrants a ticket of speeding in excess of 100 miles per hour. Well, take a look at what we know right now. We know that he traveled 5,000 feet in 30 seconds. So again, the time difference here, we're looking at miles per hour, and we know that we have feet per second. So again, we want to be able to take that value of 5,000 feet per second, and we want to be able to convert it into miles per hour. So here I'm going to be looking at the average velocity to be equal to the 5,000 feet in the 30 seconds. So I'm going to want to convert that into feet per second, similarly to what we've done previously. So I'm going to take that and multiply it by the fact that there's, in 1 mile, there's 5,280 feet. And there are 3,600 seconds in 1 hour. So looking at our units here, and I forgot my unit here, this is feet. So we have seconds and seconds simplifying, feet and feet simplifying, leaving us miles per hour. So that would give us a total of, let me go back to my purple color here, 5,000 times 3,600 divided by 5,280 will give us approximately 113.636 miles per hour. Hour. I don't know why I want to say something there. Let's see. Come on, give me my pencil back. Hour. There we go. Okay. So over the 30 seconds, his average velocity was 113.36 or 0.636 miles per hour. So how do we justify that he was traveling in excess of 100 miles per hour? Well, I'm going to pause the video and I'm going to write out my explanation, but so that way you don't have to take the time to see me writing it. So I'm going to pause the video real quick and write out my explanation. Okay, so thanks for bearing with me with the pause. But the fact that the average velocity was greater than 100 miles per hour, the mean value theorem for integrals will guarantee that Dan had to have traveled more than 100 miles per hour for at least some portion of the 30-second time interval. And that is going to wrap up the notes for applications of differential equations. Uh, thanks for watching, and I hope you learned something. But until next time, ladies and gentlemen, thanks a lot and take care.